When a massive star dies, its heart can collapse into something stranger than science fiction, a neutron star. Born from violent supernovae, these stellar remnants spin with clock-like precision, becoming cosmic timekeepers. In this video, we'll explore their mysteries and extremes. If you enjoy this journey, please like, subscribe, and share, and tell us in the comments which space mystery fascinates you most. Thank you for watching now. Let's begin. A neutron star begins its existence when a massive star ends its life in a core collapse supernova. The process unfolds inside a star that has already burned through its nuclear fuel, first hydrogen, then helium, and through successive stages until iron builds in the center. Iron does not release energy when fused, so once the star's core fills with this element, the energy balance that supports the star becomes fragile. At this moment, the inward pull of gravity outweighs the outward pressure from nuclear reactions, and the collapse begins. The collapse is sudden and violent in stellar terms, happening in less than a single second. The core, which once had a radius similar to that of Earth, shrinks rapidly to a compact object only about tens of kilometers across. The density rises until it matches that of an atomic nucleus, far beyond ordinary matter. Protons and electrons, forced into close contact, combine to form neutrons through a process called electron capture. As neutrinos stream out, they carry away a large fraction of the gravitational energy released in the collapse. This moment produces what is called a protoneutron star. The protoneutron star is briefly obscured within the stellar envelope, but the violent outward shock generated by the collapse propagates through the outer layers. The shock can stall, but neutrino heating revives it, driving the explosion that astronomers observe as a supernova. This explosion expels the outer regions of the star into space, while leaving the dense neutron-rich core behind. The newly born neutron star, at first extremely hot, glows with temperatures of hundreds of billions of degrees, and in the early seconds it emits a flood of neutrinos. These neutrinos are difficult to detect on Earth, but rare events, such as the supernova observed in 1987 in the Large Magellanic Cloud, confirm that neutrino emission plays a central role. The physical change in scale is profound. A star many times more massive than the Sun compresses its core into an object only about 20 kilometers across. To put this density into perspective, a teaspoon of neutron star matter would weigh as much as a mountain on Earth. The gravity near the surface is so intense that an object falling a single meter would strike with energy far beyond human comprehension. Yet despite this extreme gravity, the neutron star resists further collapse because of a form of pressure called neutron degeneracy pressure. This pressure arises from the Pauli exclusion principle, which prevents neutrons from occupying the same quantum state. Just as electrons in white dwarfs resist further compression, neutrons in these stars support the core against collapse into a black hole, at least up to a certain maximum mass. Astronomers have pieced together this picture from both theoretical models and direct observations of supernova remnants. When we look at the Crab Nebula, for example, we see the expanding cloud of gas and filaments that resulted from a supernova observed in the year 1054. At the center of that nebula lies a pulsar, a rapidly rotating neutron star. Its presence is evidence that the remnant core survives after the explosion. Similarly, in Cassiopeia A, another supernova remnant, X-ray observations with the Chandra Observatory have identified a compact source consistent with a cooling neutron star. Each remnant is a natural laboratory for understanding the transition from massive star to neutron star. The collapse itself is governed by a balance of forces. Gravity acts without limit, pulling the material inward. Thermal pressure, radiation pressure, and nuclear forces try to resist. But as the nuclear fuel depletes, only degeneracy pressure remains. The inward acceleration produces densities where the strong nuclear force becomes relevant on macroscopic scales, something that never occurs in ordinary matter. During this brief collapse, shock waves bounce outward when the inner core halts its fall, but whether this shock leads to a full explosion depends on delicate processes involving neutrino heating and convection. Modern three-dimensional simulations suggest that turbulence and neutrino absorption play critical roles in reviving the shock, though uncertainties remain. As the outer layers are expelled, heavy elements that were synthesized during the explosion are scattered into space. These elements include oxygen, silicon, and iron, as well as rarer isotopes forged in the high-temperature environment. This dispersal enriches the interstellar medium, seeding future generations of stars and planets. Meanwhile, the compact core settles as the outer shock moves outward. For a few seconds it is a proto-neutron star, still adjusting its internal structure. Neutrinos stream out from deep within, carrying away most of the gravitational binding energy, roughly equal to 10% of the rest mass energy of the Sun. This emission is the most powerful neutrino source known in the universe. Within less than a minute, the proto-neutron star cools enough to become a stable neutron star, its surface temperature, still reaching tens of millions of degrees, emits primarily in X-rays. The magnetic fields that thread the core, amplified during collapse, emerge at the surface with extraordinary strength, in some cases reaching trillions of times stronger than Earth's field. The rapid rotation of the star, a relic of the original angular momentum compressed into a much smaller object, sets the stage for the pulsed emissions that define pulsars. But in these first moments, the most important fact is the survival of the compact remnant itself. If the star had been significantly more massive, the collapse would have continued past the neutron degeneracy limit, forming a black hole. But within a certain mass range, the neutron star stands as the final product of stellar evolution. The observational evidence for such a process is diverse. Light curves of supernovae, when monitored over weeks, show the decay of radioactive isotopes like nickel and cobalt produced in the explosion. Spectra reveal the velocities of the expanding ejecta. Radio telescopes map the filaments of synchrotron radiation, where particles accelerate in magnetic fields. At the heart of these remnants lies the invisible or faintly glowing neutron star, detectable only in certain wavelengths. The detection of neutrinos from supernova 1987D provided direct confirmation of the theory within a span of seconds. Detectors on Earth recorded a handful of neutrinos consistent with models of core collapse. This singular event connected human instruments with processes at the very edge of stellar death. The calm understanding of this chain of events is that massive stars cannot escape the destiny imposed by their internal physics. When fusion of iron no longer yields energy, gravity overwhelms all resistance. The collapse produces conditions where quantum rules dominate on astronomical scales, and the outcome is an object unlike anything else in the cosmos. This is the birth of the neutron star, a body that compresses matter to nuclear densities, shines in neutrinos during its first seconds, and emerges as one of the densest stable states of matter in the universe. The proto-neutron star exists only for a short span of time, yet it is a critical stage in the birth of a neutron star. Immediately after the collapse halts, the inner core rebounds slightly, producing an outward shock that initially pushes against the infalling matter. However, This shock wave weakens quickly as it moves outward, losing energy to the dissociation of iron nuclei and to the outflow of neutrinos. Without an additional energy source, the shock would stall and the star would collapse entirely. Instead, the immense flood of neutrinos released by the dense core provides just enough heating in the outer layers to revive the stalled shock. This process, known as the delayed neutrino mechanism, allows the explosion to continue. Although the details of how convection, turbulence, and neutrino absorption interplay remain active areas of research, most simulations indicate that this balance of forces and energies makes the difference between a failed collapse into a black hole and a successful supernova leaving behind a neutron star. In the first seconds after formation, the proto-neutron star radiates more energy in neutrinos than the Sun will radiate in light over its entire lifetime. These neutrinos escape from a region called the neutrinosphere, where the density becomes low enough that they no longer interact strongly with matter. The emission cools the inner regions and gradually contracts the star. This cooling phase lasts tens of seconds, during which the object remains swollen compared to its final size. At the beginning it has a radius of about 50 kilometers, but by the end it contracts to about 20 kilometers. The matter inside is extremely hot and dense, filled with neutrons, protons, electrons, and neutrinos in thermal equilibrium. As neutrinos carry away energy, the interior reorganizes into layers that will define the stable neutron star. The outermost layers of the proto-neutron star still interact with the passing shock and with fallback material from the supernova. Some of this fallback matter rains back onto the surface, briefly increasing the star's mass. If too much falls back, the object may exceed the maximum mass that neutron degeneracy pressure can support, and the core will collapse again into a black hole. But within the safe mass range, the neutron star survives, and the fallback contributes only minor adjustments to its rotation and magnetic field. During this time, the crust begins to crystallize as the temperature drops below about 1 billion degrees. Electrons form a sea of degenerate matter, while nuclei arrange into dense lattices. The structure of the proto-neutron star is layered and constantly evolving. In the outer envelope, densities are lower, and matter behaves as a mixture of nuclei and free nucleons. Deeper inside, densities exceed nuclear saturation density, and neutrons dominate, although a fraction of protons and electrons remain to maintain charge balance. Neutrinos are temporarily trapped in the inner core, diffusing outward over seconds to tens of seconds. The gradual leakage of neutrinos drives cooling and sets the timeline for the transformation from proto-neutron star to stable neutron star. Observational evidence for this brief phase is indirect, since the proto-neutron star is hidden within the supernova envelope. The neutrinos detected from supernova 1987A are the clearest window into this process. Over a span of about 13 seconds, detectors on Earth recorded a sequence of neutrino arrivals consistent with theoretical predictions of cooling emission. These events, though numbering fewer than 30, confirmed that the proto-neutron star phase exists and behaves largely as expected. Modern detectors such as Super Kamiokande and IceCube are prepared for the next nearby supernova, which would produce thousands of neutrino detections and allow detailed study of the early evolution. The proto-neutron star stage also sets the initial conditions for later properties of the neutron star. The rotation rate is determined by conservation of angular momentum during collapse. If the original star rotated slowly, the remnant may spin only a few times per second. If it rotated rapidly, the remnant may reach hundreds of rotations per second. Likewise, the magnetic field is amplified by compression and by dynamo action in the turbulent interior. Fields of trillions of times Earth's field can be generated during these first seconds. The configuration of the field, whether dipolar or more complex, freezes into the crust as it cools, influencing the later behavior of the neutron star as a pulsar or magnetar. Another aspect shaped in this phase is the chemical composition of the outer layers. As the shock passes through, nuclear reactions occur that synthesize light and heavy elements. The protoneutron star atmosphere contains free neutrons and protons, which can combine to form nuclei before being ejected. These nucleosynthetic products contribute to the chemical enrichment of the supernova ejecta, adding to the broader cycle of elements in the galaxy. The conditions near the surface are extreme enough that unusual isotopes, not stable on Earth, can form and survive long enough to be detected later in supernova remnants. Simulations of the protoneutron star phase are challenging because they require modeling of neutrino transport, nuclear equations of state, and hydrodynamics all at once. Nonetheless, decades of research have produced models that broadly agree with observed neutrino signals and with the properties of young neutron stars. These models suggest that within the first minute after collapse, the object loses about 1/10 of a solar mass in energy through neutrino emission. Its temperature drops from hundreds of billions of degrees to tens of billions, and its structure solidifies into the dense, compact form we associate with neutron stars. During this cooling, convection inside the protoneutron star stirs matter, redistributing heat and composition. Such convection may also amplify magnetic fields and contribute to asymmetries in the explosion. Some observations of supernova remnants suggest that explosions are not perfectly spherical, supporting the idea that protoneutron star convection plays a role. In addition, gravitational waves may be produced by oscillations and turbulence in the early moments, though such signals remain below the sensitivity of current detectors except for the very closest events. Future gravitational wave observatories may detect the subtle ripples from this stage, adding a new window into the protoneutron star. When the neutrino emission subsides and the interior cools enough for superfluidity and superconductivity to begin, the protoneutron star becomes a stable neutron star. The transition is gradual, not marked by a single moment, but by the end of the first minute the essential features are in place. The object has a dense core of mostly neutrons, a thin crust of nuclei and electrons, and a powerful magnetic field threading its surface. Its size is fixed at around 20 kilometers across, and its mass lies between about 1 and 2 solar masses. From this point forward, it will cool slowly over millions of years, radiating primarily in X-rays and gradually spinning down as it emits electromagnetic radiation and particle winds. The protoneutron star stage is therefore a fleeting but fundamental step. It links the violent collapse of the progenitor star with the enduring presence of a neutron star. It shapes the mass, radius, rotation, and field of the remnant, and it determines whether the outcome is a neutron star or a black hole. The handful of neutrinos recorded on Earth from a single supernova provide the clearest glimpse of this process. But the quiet certainty of physics assures that every neutron star in the universe passed through this brief luminous state, radiating in neutrinos more powerfully than in any other form. When the protoneutron star stabilizes, attention turns to the nature of its matter. The densities inside exceed anything encountered in terrestrial laboratories, reaching values greater than those found in atomic nuclei. Ordinary matter consists of atoms with nuclei and electrons arranged in shells, but inside a neutron star the pressure is so great that atomic structures vanish. Nuclei dissolve, and protons combine with electrons to form neutrons through electron capture. The result is bulk matter dominated by neutrons, compressed until the separation between particles is on the order of a femtometer, the size of a single nucleon. This state is known as nuclear density matter. Physicists describe this material through what is called the equation of state. The equation of state specifies how pressure relates to density and temperature. In neutron stars, the equation of state is uncertain because the strong nuclear force governs interactions among neutrons at densities beyond those studied in accelerators. Several theoretical models exist, ranging from stiff equations that predict stars with larger radii to soft equations that predict more compact stars. Observations of neutron star masses and radii provide the primary way to constrain these models. For example, the detection of neutron stars with masses around 2 times that of the Sun demonstrates that the equation of state must be stiff enough to support such objects against collapse. If the equation of state were too soft, no neutron star could reach that mass without becoming a black hole. The central density of a neutron star may be several times the nuclear saturation density, which is the density at which nucleons in nuclei are packed most closely on Earth. At these densities, matter may not remain as neutrons and protons. Theoretical possibilities include the appearance of hyperons, which are particles containing strange quarks, or even a transition to quark matter, where individual neutrons dissolve into their constituent quarks. Such exotic phases remain speculative, but they are consistent with some models of the strong interaction. Astronomers cannot yet determine whether these phases exist, but they continue to test the predictions using astronomical observations. One way to probe the equation of state is through measurements of neutron star radii. Instruments such as the NICER telescope aboard the International Space Station use X-ray timing to observe hotspots on rotating neutron stars. The precise shape of the light curves depends on how strongly the star's gravity bends light near the surface, which in turn depends on the mass-to-radius ratio. From such observations, researchers have inferred radii of about 12 kilometers for stars of about 1.5 solar masses. These measurements rule out some equations of state that predict very large or very small radii, narrowing the possibilities for the structure of dense matter. Another probe comes from gravitational waves emitted during neutron star mergers. When 2 neutron stars spiral together, their shapes are distorted by tidal forces. The degree of distortion depends on the stiffness of their matter, quantified by a property called tidal deformability. The LIGO and Virgo detections of the binary merger in 2017 provided constraints on tidal deformability that suggest neutron stars are neither extremely stiff nor extremely soft. This again points to radii around 10 to 14 kilometers, consistent with X-ray observations. Laboratory experiments also contribute, though they cannot reach neutron star densities directly. Heavy ion collisions at facilities such as the relativistic Heavy Ion Collider and the Facility for Antiproton and Ion Research create short-lived states of dense nuclear matter. By comparing experimental results with theoretical models, physicists refine their understanding of the strong nuclear force, which can then be extrapolated to neutron star conditions. However, uncertainties remain large, and direct astronomical measurements are indispensable. The physics of nuclear density matter also determines the maximum mass a neutron star can sustain. If the mass exceeds a certain value, gravity overwhelms degeneracy pressure and nuclear forces, and the star collapses into a black hole. This maximum mass depends directly on the equation of state. Current observations of heavy neutron stars near 2 solar masses set a lower limit, while theoretical considerations suggest an upper limit of perhaps 2.5 to 3 solar masses. No neutron stars heavier than this range are expected to exist in stable form. This threshold is critical for interpreting the outcomes of binary mergers, where the remnant may be a heavier neutron star or may collapse immediately into a black hole. Inside the star, the matter is stratified. The crust contains nuclei in a lattice with degenerate electrons, gradually transitioning to regions where free neutrons drip out. At greater depth, the density reaches nuclear values, and matter becomes a uniform fluid of neutrons with a small fraction of protons and electrons. Deeper still, exotic possibilities arise, but their presence remains unconfirmed. Theoretical studies also suggest that at the crust-core boundary, nuclei may arrange into unusual shapes known as nuclear pasta, resembling sheets or rods. These configurations minimize energy under extreme conditions and influence how heat and neutrinos move through the crust. Cooling studies of young neutron stars provide another indirect probe of dense matter. The rate at which a star cools depends on which neutrino emission processes are allowed in its core. If direct Urca processes, involving rapid neutrino emission by protons and neutrons, occur, the star cools faster. If only modified Urca processes are permitted, cooling is slower. Observations of surface temperatures of young neutron stars compared with theoretical cooling curves allow astronomers to test which processes are active, which in turn depends on the composition of the core. Some neutron stars appear to cool rapidly, hinting that exotic particles or phases may indeed be present. The behavior of dense matter also affects observable features such as starquakes, glitches, and oscillations. The rigidity of the crust and the elasticity of deeper layers determine how stresses build and release. A stiff equation of state produces stronger crusts capable of supporting larger deformations, which may affect the amplitude of gravitational waves from rotating neutron stars. These subtle signals, though not yet detected, represent future opportunities to measure the equation of state in new ways. Thus, this study of nuclear density matter in neutron stars is both a theoretical challenge and an observational pursuit. Physicists seek to understand the strong force under conditions far beyond the reach of terrestrial experiments. Astronomers provide critical data by measuring masses, radii, cooling rates, and gravitational waves. The dialogue between these approaches gradually narrows the range of possibilities. While uncertainties remain, the emerging picture is that neutron stars contain matter at densities several times nuclear saturation, that they have radii of about 12 kilometers, and that their maximum masses are around 2 to 2.5 solar masses. The precise details of their internal composition remain unknown, but each new observation brings us closer to resolving the physics of one of nature's most extreme laboratories. A central property of neutron stars is the maximum mass they can support against further collapse. This limit arises from the balance between gravity, which always pulls matter inward, and the internal pressure of dense nuclear matter, which pushes outward. In white dwarfs, the relevant balance is between gravity and electron degeneracy pressure, and there the maximum stable mass is about 1.4 times the mass of the Sun, known as the Chandrasekhar limit. For neutron stars, the corresponding balance involves neutron degeneracy pressure and nuclear forces at supranuclear densities. Unlike white dwarfs, the strong interaction plays a major role, and the maximum mass depends sensitively on the equation of state of dense matter. Observations of massive neutron stars provide some of the clearest constraints on this problem. In 2010, precise radio timing of the pulsar PSR J4 showed it had a mass close to 2 solar masses. Later, the pulsar JR348-0432 was also measured at just over 2 solar masses. More recently, measurements of JR740-62 placed its mass at about 2.1 solar masses. These stars confirm that the maximum mass must be at least as high as these observed values. Any theoretical model of the equation of state that cannot support such stars is ruled out. Thus, the data suggest a maximum mass somewhere between about 2.5 and 3 solar masses. Above this range, the inward pull of gravity overwhelms all known forces, and the star must collapse into a black hole. The maximum mass is not only a question of static balance, but also of rotational effects. Rapid rotation adds centrifugal support, allowing a neutron star to remain stable at a slightly higher mass than it could if it were not rotating. This increase is modest, perhaps up to about 20% depending on spin rate. However, over time, neutron stars lose angular momentum through electromagnetic radiation and particle winds, so any star initially stabilized by rotation will eventually slow down. When it passes the stability threshold, it collapses into a black hole. Such delayed collapses may occur after binary mergers, when the remnant is briefly supported by rapid rotation and thermal pressure before cooling and spin-down drive it past the maximum mass. Understanding these limits is crucial for interpreting observations of gravitational waves from neutron star mergers. In the event detected in 2017, known as G770817, two neutron stars collided and formed a transient remnant. The afterglow suggested that the remnant did not survive long as a stable neutron star but collapsed into a black hole. The total mass of the system was about 2.7 solar masses, which is consistent with the idea that the maximum stable mass lies below this value for non-rotating stars. Observations of such mergers thus provide indirect but powerful evidence for the maximum mass of neutron stars. The stability limit also has implications for the fate of massive stars at the end of their lives. When the core of a collapsing star exceeds the neutron star maximum mass, no stable neutron star can form. Instead, the collapse continues into a black hole, often accompanied by little or no visible supernova. This pathway is sometimes called a failed supernova, and evidence for such events comes from observations of massive stars disappearing without bright explosions. In these cases, the maximum mass of neutron stars defines the dividing line between visible core collapse supernovae that leave behind neutron stars and invisible collapses that produce black holes. The determination of the maximum mass is linked to other observable properties such as radius and deformability. A stiffer equation of state can support heavier stars with larger radii, while a softer equation of state produces lighter stars with smaller radii. As a result, measurements of one property constrain the others. For example, if radii are close to 12 kilometers, as suggested by NISA observations, then the maximum mass is likely between about 2.5 and 3 solar masses. If future measurements were to reveal a neutron star with mass above this range, it would imply that dense matter is stiffer than currently thought. Conversely, if no such massive stars are ever found, it would confirm the lower range of possibilities. The limit also plays a role in the possible existence of more exotic compact objects. Some theories propose that under extreme conditions matter might transition into strange quark matter, a state where up, down, and strange quarks exist freely rather than confined into nucleons. In such a case, an entire star made of strange quark matter, sometimes called a strange star, could exist with different stability properties. However, no clear observational evidence for such objects has been found. The known population of neutron stars fits within the expected range of masses and radii for ordinary nuclear matter, so the standard picture remains the consensus. From a physical standpoint, the reason neutron stars cannot support unlimited mass is that gravity increases with mass more strongly than pressure does. As more matter is added, the inward pull rises faster than the resisting force. At some point, the neutrons are packed so closely that adding more mass does not increase pressure enough to balance gravity. Beyond this point, collapse is inevitable. This reasoning is rooted in general relativity, which shows that gravity itself contributes to the total energy and pressure in the system. As the star becomes more compact, space-time curvature becomes extreme, and even the strongest known interactions cannot counteract it. Astronomers study these limits not only for their intrinsic interest, but also for their role in astrophysical processes. The maximum mass determines the types of compact remnants produced by stellar evolution, the outcomes of mergers, and the sources of gravitational waves. It sets the boundary between neutron stars and black holes, which in turn affects how galaxies evolve through their populations of compact objects. The ongoing effort to refine the value of the maximum mass involves radio timing of pulsars, X-ray observations, gravitational wave detections, and theoretical modelling of nuclear physics. Each approach adds a piece to the puzzle, narrowing the uncertainty. In practical terms, the most massive neutron stars known today provide the clearest anchor. With reliable measurements above 2 solar masses, the lower bound is firmly established. The upper bound remains less certain, but is constrained by the lack of observed neutron stars above 3 solar masses and by models of binary merger remnants. As detectors improve, future observations will tighten these limits, gradually revealing the precise point at which neutron stars give way to black holes. Until then, the maximum mass remains a key frontier in the study of dense matter and compact objects, linking the physics of the nucleus to the behavior of stars on cosmic scales. Once a neutron star has passed through its proto-stage and reached stability, it begins a long process of thermal evolution. Unlike ordinary stars, neutron stars no longer generate energy through nuclear fusion. Their luminosity comes from residual heat left over from formation and from ongoing processes such as neutrino emission and photon radiation. In the earliest moments after birth, the neutron star is extremely hot, with interior temperatures of hundreds of billions of degrees. Most of this energy is released as neutrinos, which escape directly from the dense matter. Within about 1 minute, the star has cooled by several orders of magnitude, and its surface temperature falls to tens of millions of degrees. The cooling process can be described in stages. In the first 10 to 100 years, the core temperature drops rapidly because neutrino emission is extremely efficient. Neutrino production occurs through a variety of mechanisms. The most powerful is the direct Urca process, in which a neutron decays into a proton, electron, and neutrino, or a proton combines with an electron to form a neutron and an antineutrino. Whether this process operates depends on the fraction of protons present in the core. If the fraction is high enough, direct Urca reactions are allowed and the star cools quickly. If not, cooling proceeds more slowly through the modified Urca process, which requires an additional bystander particle to conserve momentum. Other processes, such as neutrino emission from bremsstrahlung during nucleon collisions, and from Cooper pair formation when neutrons become superfluid, also contribute. After about 100 to 1000 years, the neutrino cooling stage begins to give way to photon cooling. The surface temperature, still in the range of millions of degrees, radiates primarily in X-rays. During this time, telescopes such as Chandra and XMM Newton can detect thermal emission from young neutron stars, providing direct data on their surface temperatures. These measurements are compared with theoretical cooling curves to test which processes are active in the core. For example, The neutron star in Cassiopeia A has shown a surface temperature decline over a decade of observations, suggesting the onset of neutron superfluidity in its core. When neutrons pair up into superfluid states, they release bursts of neutrinos as pairs form, leading to enhanced cooling. This observation provides rare evidence for exotic states of matter in neutron star interiors, on timescales of thousands to millions of years. Photon cooling dominates. The surface temperature gradually declines from millions of degrees to hundreds of thousands of degrees. At these stages, the neutron star's thermal emissions shift from X-rays to ultraviolet and optical wavelengths. Though most stars are too faint to detect at such low temperatures, only the youngest and closest neutron stars can be observed directly in this regime. As time advances further, the stars become too cool and dim to detect thermally, and their visibility depends instead on non-thermal processes such as magnetospheric emission or accretion from a companion. The thermal evolution depends on several factors, including the mass of the neutron star, the composition of its envelope, and the presence of magnetic fields. A thin layer of light elements such as hydrogen or helium in the outer envelope can enhance heat transport, leading to a higher surface temperature for the same core temperature. By contrast, heavy element envelopes insulate the core more strongly. Magnetic fields also affect heat conduction by channeling it along field lines. This can produce anisotropic surface temperatures, with hotter regions near the magnetic poles and cooler regions elsewhere. Observations of pulsars that show thermal X-ray emission often reveal such hotspots, consistent with the influence of strong fields on thermal transport. Another important aspect is reheating. While most of the cooling is passive, some processes can add heat back into the star. For example, the decay of strong magnetic fields, particularly in magnetars, releases energy that heats the crust and can maintain high surface temperatures for tens of thousands of years. Similarly, frictional heating from differential rotation between superfluid components inside the star and the solid crust can add heat. Accretion from a binary companion can also deposit energy, temporarily raising surface temperatures and resetting the cooling track. These reheating processes complicate the picture but also provide additional observational signatures. The study of neutron star cooling is not just about temperature decline. It also provides a unique probe of the physics of dense matter. The rate of cooling depends directly on which neutrino processes are active, which in turn depends on the composition and state of matter in the core. By comparing observed surface temperatures of neutron stars of different ages with theoretical predictions, researchers can constrain whether direct Urca processes occur, whether neutrons and protons are superfluid or superconducting, and whether exotic particles such as hyperons or quarks are present. Each cooling curve becomes a test of fundamental physics under conditions unreachable in laboratories. Young neutron stars less than 1 million years old provide the clearest data because they are still warm enough to emit detectable thermal radiation. Examples include the neutron star in Cassiopeia A, the Vela pulsar, and the so-called Magnificent Seven, a group of nearby isolated neutron stars discovered in X-rays. These stars display a range of surface temperatures, suggesting differences in mass, magnetic field, and envelope composition. By building a sample of such objects, astronomers gradually piece together how cooling varies across the neutron star population. Over longer timescales, neutron stars become effectively invisible thermally. After about 10 million years, their surface temperatures fall below 100,000 degrees, making them too faint to detect with current instruments. At this point, their detectability relies on non-thermal processes, such as pulsed radio emission or X-ray emission from magnetospheric currents. Some may still be visible if they accrete matter from the interstellar medium, but most simply fade from view. This means that the observable sample of cooling neutron stars is limited to relatively young ages, and reconstructing the full cooling history requires careful modelling. Theoretical work continues to refine cooling models, incorporating advances in nuclear physics, superfluidity theory, and neutrino emission mechanisms. Cooling curves are calculated for different assumptions about the core composition and compared with observational data. Discrepancies between prediction and observation highlight missing physics, such as the role of nuclear pasta in the crust, or the effects of strong magnetic fields on heat transport. The ongoing effort reflects the close link between astrophysical observation and fundamental nuclear theory. In summary, the thermal evolution of neutron stars unfolds in well-defined stages governed by neutrino emission and photon radiation. It transforms an initially blazing hot remnant into a faint, cold object over millions of years. Along the way, the details of cooling reveal critical information about dense matter, superfluid states, and magnetic processes. Each observation of a cooling neutron star provides a piece of evidence for the physics that operates at densities many times that of atomic nuclei, offering a quiet but profound glimpse into matter at its most extreme. The crust of a neutron star forms as the hot proto-neutron star cools and solidifies. It is a thin outer layer by stellar standards, but its structure is complex and its properties shape many observable features of neutron stars. The crust extends from the surface down to densities near nuclear saturation, about 10 to the 14th grams per cubic centimetre. At the very top is a thin atmosphere only a few centimetres thick, composed of light elements such as hydrogen or helium, if they remain after the explosion or are accreted later, or heavier elements if lighter ones are stripped away. This atmosphere emits thermal radiation, which escapes directly into space. The spectrum of this emission, when measured with X-ray telescopes, allows astronomers to estimate surface temperatures and, in some cases, to infer the presence of particular elements. Beneath the atmosphere lies the outer crust, where electrons are degenerate and nuclei exist in a crystalline lattice. The pressure squeezes atoms so tightly that electrons are no longer bound to nuclei, forming a sea of free electrons that carry current and transport heat. The nuclei become increasingly neutron-rich with depth, as electron capture processes convert protons into neutrons. The lattice structure of the crust is thought to be extremely strong, with a shear modulus far greater than that of terrestrial materials. This rigidity allows the crust to support mountains only centimetres high in absolute terms, but these small deformations are significant in the extreme gravity and may lead to continuous gravitational wave emission from rotating stars. Deeper still is the inner crust, where densities exceed the threshold for neutron drip. In this regime, free neutrons leak out of nuclei and form a superfluid permeating the lattice. This mixture of neutron-rich nuclei, free neutrons, and electrons has unusual properties. The interaction between the superfluid and the lattice is believed to play a role in pulsar glitches, sudden changes in rotation rate observed in many neutron stars. The inner crust thus provides a dynamic connection between microscopic quantum states and macroscopic astrophysical phenomena. As density increases further, the structure of nuclei changes in unexpected ways. Rather than spherical nuclei, matter may arrange into elongated rods, flat sheets, or other exotic shapes collectively known as nuclear pasta. These structures minimize energy under extreme conditions and resemble lasagna or spaghetti when modelled, though the terms are only descriptive. Nuclear pasta influences how heat and neutrinos move through the crust, and it may affect the star's magnetic field evolution. Because direct observation of nuclear pasta is impossible, its presence is inferred from theoretical modelling and from indirect effects on cooling and crust oscillations. The boundary between crust and core occurs when nuclei dissolve completely, and matter becomes a uniform fluid of neutrons with a small fraction of protons and electrons. This transition marks the end of the crust and the beginning of the dense core. Yet the crust, though thin, is central to many observable behaviors. For example, thermal X-ray emission from cooling neutron stars passes through the crust, so the thermal conductivity and composition of the crust control the observed surface temperature. Differences in envelope composition can produce large variations in surface brightness, even for stars with identical core temperatures. The crust also plays a role in magnetic field evolution. The magnetic field of a neutron star is anchored in currents within the crust and core. Over long timescales, the resistivity of crustal matter and the movement of superfluid neutrons affect how the field decays. Magnetars, neutron stars with especially strong magnetic fields, show bursts and flares thought to be triggered by crustal fractures. When stresses from evolving magnetic fields exceed the breaking strain of the crust, starquakes occur, releasing energy observable as sudden X-ray or gamma-ray bursts. These events highlight the mechanical strength of the crust and the extreme conditions it endures. Astronomers probe the crust using several observational techniques. X-ray timing of pulsars provides evidence for hotspots on the surface, shaped by magnetic channels that pierce the crust. Thermal afterglows following magnetar flares reveal how heat diffuses through the crust. Observations of quasi-periodic oscillations in magnetar outbursts have been interpreted as seismic vibrations of the crust, providing a form of neutron star seismology. These oscillations carry information about the crust's elasticity and thickness, though interpretation is complicated by coupling between crust and core. Accreting neutron stars in binary systems also reveal properties of the crust. As matter from a companion star accumulates on the surface, it undergoes thermonuclear burning, producing X-ray bursts. Over longer timescales, the added mass compresses the crust, driving nuclear reactions at increasing depth. These reactions release heat that can be observed when accretion halts and the crust cools back into equilibrium with the core. Monitoring this cooling provides insight into the thermal conductivity and heat capacity of the crust. Such studies have shown that neutron star crusts conduct heat extremely efficiently, confirming theoretical predictions. The crust's importance extends to the stability of the star as a whole. Though only about 1% of the mass resides in the crust, its rigidity allows it to store and release stress. This is especially relevant for rotation. As the star spins down, stresses build in the crust until they're relieved by small shifts or fractures, which may explain sudden jumps in rotational frequency. The crust therefore mediates between the deep core, where superfluids dominate, and the magnetosphere, where electromagnetic radiation is produced. Future observations may refine our understanding of crustal physics. X-ray missions such as NISA continue to measure surface emission with high precision. Gravitational wave detectors may one day observe continuous emission from neutron stars with small deformations in their crusts. Theoretical models are improving with advances in nuclear physics, providing better descriptions of matter at crustal densities. Together, these efforts aim to build a coherent picture of how the crust forms, evolves, and interacts with the rest of the star. In summary, the crust of a neutron star is not a simple shell, but a dynamic and layered structure. From the thin atmosphere to the outer crust lattice, through the neutron-rich inner crust and possible nuclear pasta, it connects the surface we observe with the dense core beneath. Its properties influence cooling, magnetic field evolution, seismic activity, and rotational stability. Though only a fraction of the star, the crust is essential to understanding how neutron stars behave, how they radiate, and how they evolve over time. Deep inside a neutron star, beneath the crust and outer layers, conditions become even more extreme. The densities rise beyond nuclear saturation, and the behavior of matter changes in fundamental ways. One of the most remarkable predictions is that neutrons in the core do not remain in a simple fluid state, but instead form a superfluid. Likewise, the small fraction of protons present can become a superconductor. These exotic states arise because particles at such high densities and low temperatures can undergo quantum pairing, similar in principle to the way electrons form Cooper pairs in terrestrial superconductors. In a neutron star, however, the scales are vastly more extreme, with entire stellar interiors behaving as coherent quantum systems. The concept of superfluidity in neutron stars was proposed in the 1950s, not long after the discovery of superfluid helium in laboratory experiments. In a superfluid, particles pair up and move without viscosity. This means that the neutron fluid inside the star can flow without resistance, allowing it to circulate freely through the dense core. The transition to superfluidity occurs when the temperature drops below a critical value, typically about 1 billion degrees. For a neutron star, this happens within the first 100 years of its life as it cools. Evidence for neutron superfluidity comes from observations of rapid cooling in young stars, such as the neutron star in Cassiopeia A, whose temperature decline has been interpreted as a signal of neutron pairing. The protons, although much less abundant than neutrons, also play an important role. Under the same extreme conditions, they can form Cooper pairs and become superconducting. A superconducting fluid of protons can carry electric currents without resistance. Since the magnetic field of a neutron star is supported by currents in its interior, superconductivity has profound implications for the evolution of the magnetic field. In Type II superconductors, magnetic flux penetrates the fluid in quantized tubes known as fluxoids. These fluxoids interact with the neutron superfluid and the solid crust, creating a complex system that couples the dynamics of rotation and magnetism. The combination of superfluid neutrons and superconducting protons gives rise to a layered structure of quantized vortices and flux tubes. In a rotating superfluid, angular momentum is not distributed smoothly, but concentrated into quantized vortex lines. The number and spacing of vortices depend on the rotation rate of the star. As the neutron star gradually loses angular momentum and slows its rotation, these vortices must move outward and annihilate. However, if they pin to the crust or to magnetic flux tubes, they can become stuck. Stress builds until the vortices suddenly unpin, transferring angular momentum abruptly to the crust. This process is the leading explanation for pulsar glitches, the sudden spin-ups observed in many neutron stars. Observationally, glitches provide indirect evidence for the presence of a superfluid. Pulsars such as the Vela pulsar show large glitches roughly every few years, with sudden increases in spin frequency followed by gradual relaxation. These events are interpreted as the response of the crust to angular momentum transfer from the interior superfluid. The details of how vortices pin and unpin remain under study, but the broad agreement between theory and observation strongly supports the existence of superfluid components in neutron stars. Superconductivity also leaves signatures. The evolution of magnetic fields in neutron stars is slower than it would be if the protons were an ordinary fluid. The presence of quantized flux tubes in a superconducting medium alters how magnetic fields decay and move. In magnetars, stresses associated with flux tube motion may contribute to crustal fractures and bursts. In ordinary pulsars, superconductivity helps explain the long-term persistence of magnetic fields over millions of years. Models that include superconducting protons provide better agreement with observed field strengths and decay rates. The existence of superfluid and superconducting matter also affects the cooling of neutron stars. When neutrons or protons form pairs, they emit neutrinos in a process known as Cooper pair breaking and formation. This provides an additional cooling channel at the moment when superfluidity sets in, leading to observable rapid cooling. Conversely, once pairing is established, neutrino emission from ordinary processes is suppressed because paired particles cannot participate as easily in reactions. The overall effect is a distinctive cooling curve that matches some observed neutron star temperatures. Thus, thermal evolution provides indirect evidence for both neutron superfluidity and proton superconductivity. Beyond cooling and glitches, the quantum states of the core may influence oscillations and gravitational waves. Superfluidity changes the way sound waves and oscillations propagate through the star. The presence of vortices and flux tubes adds rigidity and alters how the star responds to stresses. In principle, these changes could affect the gravitational wave signals emitted during starquakes or binary mergers, though current detectors cannot resolve such details. Future observations may provide further constraints on the interior physics. Theoretical work on superfluidity and superconductivity in neutron stars continues to advance. Nuclear physics calculations estimate the critical temperatures for pairing and the energy gaps involved. Supercomputer simulations attempt to model how vortices move and interact with flux tubes and crustal nuclei. Laboratory studies of ultra-cold atomic gases, where fermions pair into superfluid states, provide useful analogies, though the densities are vastly lower. Together, these approaches build a consistent picture of quantum states in dense matter. One of the intriguing consequences of this physics is that a neutron star, despite being macroscopic in size, behaves in some respects like a giant atomic nucleus, and in other respects like a laboratory for condensed matter physics. It combines nuclear forces, quantum mechanics, and astrophysics in a single object. The coexistence of neutron superfluidity and proton superconductivity shapes many of the observable features that astronomers measure, from spin irregularities to magnetic field persistence to thermal emission. Each new observation of glitches, cooling, or magnetic activity provides another test of these ideas. In conclusion, the core of a neutron star is not an inert fluid but a dynamic quantum system. Neutrons flow as a superfluid, protons carry currents as a superconductor, and the interactions between vortices and flux tubes couple the star's rotation and magnetism. This remarkable state of matter underlies many of the phenomena that make neutron stars such compelling objects to study. It demonstrates how quantum mechanics, discovered to describe the microscopic world, governs the behavior of entire stars under the most extreme conditions in the universe. Among the most striking features of neutron stars are their magnetic fields. These fields are not only strong but reach values beyond those seen anywhere else in the universe. Typical pulsars have surface magnetic fields of about 1 trillion times that of Earth, while a special class known as magnetars reach fields of up to 1,000 times stronger still. Such fields dominate the physics of the outer layers, control the emission of radiation, and in extreme cases produce bursts of high-energy light that can briefly outshine all other X-ray sources in the sky. The origin of these fields lies in the amplification processes that occur during the collapse of the progenitor star. A main sequence star may begin with a modest magnetic field. As the core collapses from thousands of kilometers to only tens of kilometers, conservation of magnetic flux increases the field strength by many orders of magnitude. In addition, turbulent motion and differential rotation during the proto-neutron star stage can drive dynamo action, further amplifying the field. The outcome is a compact star with an immensely powerful and organized magnetic field frozen into its crust and core. Once established, the magnetic field governs much of the star's behavior. Charge particles in the outer layers are constrained to move along magnetic field lines, shaping the structure of the magnetosphere. Radiation is channeled into beams that sweep through space as the star rotates. In magnetars, the energy stored in the field exceeds the rotational energy, making magnetic decay the dominant power source. The stresses from the field deform the crust, and when the strain exceeds the breaking strength, starquakes occur. These quakes release energy that heats the crust and powers bursts of X-rays and gamma rays. The giant flares observed in 1979, 1998, and 2004 from different magnetars are examples of this process, each releasing more energy in a fraction of a second than the Sun emits in hundreds of thousands of years. The decay of magnetic fields is a slow but significant process. Ordinary pulsars with weaker fields show little decay over millions of years, while magnetars with the strongest fields exhibit noticeable evolution over tens of thousands of years. The decay occurs through several mechanisms, including ohmic diffusion, where electric currents dissipate due to the finite resistivity of crustal matter, and ambipolar diffusion, where charged and neutral particles move differently in the core. Hall drift, a nonlinear process in which currents and fields interact, can also rearrange field structures. Together, these processes determine the lifetime of strong fields and influence how neutron stars evolve across different observational categories. Astronomers classify neutron stars partly by their magnetic behavior. Rotation-powered pulsars are sustained by the conversion of rotational energy into radiation through their magnetospheres. Magnetars are powered primarily by magnetic field decay. Millisecond pulsars, with weak fields of about 100 million times Earth's field, are old stars that have been spun up by accretion from a companion. The diversity of observed neutron stars thus reflects the interplay between magnetic field strength, rotational energy, and environment. Observations across the electromagnetic spectrum reveal the imprint of magnetic fields. In radio pulsars, the beamed emission is aligned with magnetic field geometry, and polarization measurements trace the orientation of the field. In X-rays, thermal hotspots correspond to regions where field lines funnel returning currents onto the surface. In magnetars, bursts and flares in X-ray and gamma-ray bands directly reflect magnetic stress release. In some cases, X-ray spectra show features interpreted as cyclotron lines, produced by charged particles spiraling in strong fields. These features provide direct measurements of magnetic field strength, confirming theoretical estimates. Magnetic fields also influence how neutron stars cool. Strong fields modify heat conduction, channeling it along field lines and producing anisotropic surface temperatures. This results in hotspots near the magnetic poles and cooler equatorial regions. Observations of surface emission often reveal such anisotropies. Moreover, magnetic decay itself injects heat into the crust, prolonging the thermal visibility of magnetars well beyond that of ordinary pulsars. Without such heating, magnetars would fade quickly, but instead they remain detectable as bright X-ray sources for tens of thousands of years. The interaction of magnetic fields with rotation produces phenomena such as braking. As the star emits radiation and wins from its magnetosphere, it loses rotational energy. The rate of spin down depends directly on the magnetic field strength. By measuring the period of pulsar rotation and its derivative, astronomers can estimate the dipole field strength. This simple method, though approximate, has provided magnetic field estimates for thousands of pulsars. Building a statistical picture of the population, most fall into the range of 100 billion to 10 trillion Gauss, while magnetars extend up to about 1 quadrillion Gauss. Theoretical work continues to explore the stability and evolution of magnetic fields in neutron stars. Numerical simulations model how fields rearrange under the combined influence of Hall drift and ohmic decay. These studies suggest that magnetars are born with complex field configurations that evolve rapidly, leading to stresses and bursts. Ordinary pulsars may have simpler fields that persist longer. Observations of field decay rates compared with population ages support this view, though uncertainties remain. Magnetic fields also connect neutron stars to their environments. Pulsar wind nebulae, such as the Crab Nebula, are powered by outflows of relativistic particles guided by magnetic fields. These nebulae shine brightly in synchrotron radiation, a direct result of electrons spiraling in strong fields. In binary systems, magnetic fields control how accreted matter flows onto the surface, shaping the pattern of X-ray emission. In magnetars, fields may accelerate particles to high energies, producing persistent emission that extends into the hard X-ray and soft gamma-ray bands. Looking ahead, future observations promise to refine our understanding of neutron star magnetism. X-ray polarimetry missions, such as the Imaging X-ray Polarimetry Explorer, provide direct probes of field geometry by measuring how X-rays are polarized in strong magnetic fields. Radio telescopes continue to map polarization sweeps in pulsars, tracing magnetic configurations. Gravitational wave observatories may one day detect signals from magnetically deformed neutron stars, offering yet another window on field strength. Each technique adds a piece to the puzzle of how magnetic fields arise, evolve, and ultimately decay. In summary, the magnetic fields of neutron stars are both extreme and central to their behavior. They originate from flux conservation and dynamo action during collapse, reach intensities trillions of times stronger than Earth's, and drive diverse phenomena from pulsar beaming to magnetar flares. Their evolution through decay processes shapes the lifetimes of neutron star classes, and their influence pervades cooling, emission, and interactions with the environment. To study neutron stars is therefore to study magnetism at its most powerful, revealing how fundamental physical laws play out on scales that challenge both theory and observation. Rotation is one of the most fundamental properties of neutron stars. When a massive star collapses, conservation of angular momentum dictates that its core spins up as its radius shrinks from thousands of kilometers to only about 20 kilometers. The same principle that causes a spinning skater to turn faster when pulling in her arms applies on a vastly larger scale. As a result, newborn neutron stars can rotate many times per second. Some of the fastest observed pulsars spin hundreds of times per second, making them among the most rapidly rotating objects known. The rotation of a neutron star is not constant over cosmic timescales. As it emits radiation and winds of particles from its magnetosphere, it loses rotational energy. This gradual slowing is called spin down. The loss of energy is primarily due to the torque exerted by the rotating magnetic field. The star acts like a gigantic dynamo, generating electromagnetic radiation that carries away angular momentum. The rate of slowdown depends on the strength of the magnetic field and the spin period. Stronger fields and faster spins produce more rapid losses. For ordinary pulsars, the typical timescale for significant spin-down is millions of years. Astronomers measure spin-down by carefully timing the pulses of radiation emitted by pulsars. Each pulse corresponds to one rotation of the neutron star. Over years of observation, the tiny changes in period accumulate and reveal the star's breaking. By comparing the period and its derivative, astronomers estimate both the magnetic field strength and the so-called characteristic age, a measure of how long the pulsar has been spinning down. Although not a perfect clock, this method provides approximate ages that often agree with independent estimates from supernova remnants. The energy lost during spin-down is not wasted but powers a range of astrophysical phenomena. In pulsars, the rotational energy sustains beams of radio, X-ray, and gamma-ray emission. In some cases, it also powers pulsar wind nebulae, where energetic particles flow out into surrounding space, creating luminous bubbles of synchrotron radiation. The Crab Nebula is a classic example, where the central pulsar injects enough energy to keep the nebula shining centuries after the original supernova. The link between spin-down power and observed emission allows astronomers to distinguish between rotation-powered pulsars and other neutron star types such as magnetars. Rotation is also linked to alignment between the magnetic and rotational axes. If the two axes are misaligned, beams of radiation sweep across space, and an observer sees pulses when the beam crosses Earth. The shape and intensity of the pulses depend on the geometry of this alignment. Over long timescales, magnetic torques may gradually align the axes, reducing pulse intensity. Thus, rotation not only powers emission, but also determines its geometry. An intriguing aspect of rotation is the wide distribution of observed spin periods. Young pulsars typically rotate a few times per second, reflecting their birth conditions. As they age, they slow to periods of seconds or longer. At the other extreme, old neutron stars in binary systems can be spun up by accretion of matter from a companion. These so-called millisecond pulsars rotate hundreds of times per second and are remarkably stable. Their stability makes them useful for precision timing experiments, including the search for low-frequency gravitational waves through pulsar timing arrays. Thus, rotation connects the life history of a neutron star to its observable properties. The physics of spin-down is not fully captured by the simple magnetic dipole model. Observations show that breaking indices, which describe how spin-down rate depends on period, often differ from the predicted value of 3 for pure dipole radiation. This suggests that other processes, such as particle winds or changes in magnetic field structure, also play roles. Some pulsars show irregularities in their spin-down, reflecting sudden adjustments in their internal dynamics. These features complicate models but also provide clues to the physics of the interior. Rotational energy also plays a role in explosive phenomena. In rare cases, newly born neutron stars with extremely rapid rotation and strong magnetic fields, sometimes called magnetars or hypermagnetized pulsars, may deposit rotational energy into their supernova ejector or gamma-ray bursts. This energy injection can shape the brightness and evolution of the explosion. Though such events are rare, they highlight the range of outcomes linked to initial spin. Rotation further influences gravitational wave emission. If a neutron star is not perfectly spherical, its rotation produces continuous gravitational waves. The size of such distortions depends on the strength of the crust and the magnetic field. Though no continuous gravitational waves have yet been detected, upper limits from observatories such as LIGO already constrain the degree of asymmetry in some pulsars. Future detections could provide direct evidence for small mountains on neutron stars only centimeters high, but producing measurable ripples in space-time. The connection between spin and magnetic field also explains the population distribution of neutron stars. Strong field magnetars tend to spin down quickly and are observed only at young ages. Ordinary pulsars with weaker fields live longer and populate the galaxy in larger numbers. Millisecond pulsars represent the old survivors that have been recycled through accretion. This distribution reflects the interplay of spin, magnetic field, and environment across billions of years. Spin measurements also allow astronomers to probe fundamental physics. The fastest known pulsar spins about 700 times per second. This is close to the theoretical limit at which centrifugal force would tear the star apart. The fact that no pulsars spin much faster suggests that some mechanism halts further acceleration, perhaps gravitational wave emission or magnetic braking during accretion. Thus, the fastest rotators reveal the boundary conditions for stability. In conclusion, the rotation of neutron stars is central to their identity. Born from angular momentum conservation during collapse, spin powers emission, drives nebulae, and governs observational categories. Spin down reveals magnetic field strengths and characteristic ages, variations in rotation, from young pulsars to millisecond pulsars, trace evolutionary paths. Irregularities such as glitches and braking indices provide windows into the interior. Gravitational wave searches extend the reach of rotation studies to new domains. Together, these threads make rotation one of the defining and most informative aspects of neutron star physics. Not all neutron stars rotate smoothly. Many exhibit sudden and unpredictable changes in their spin, known as glitches. A glitch is observed as a sudden increase in the rotation frequency of a pulsar, often followed by a gradual relaxation back toward the expected spin-down trend. These events, first detected in the Vela pulsar in the late 1960s, provide critical clues to the interior structure of neutron stars. They demonstrate that the star's crust and superfluid interior are not perfectly coupled, and that angular momentum can be exchanged between different components. The prevailing explanation for glitches involves the behavior of superfluid neutrons in the inner crust. In a rotating superfluid, angular momentum is carried by quantized vortices. These vortices are pinned to the lattice of nuclei in the crust, preventing them from moving outward as the star gradually slows down. Over time, the differential rotation between the pinned superfluid and the crust builds up. When the stress reaches a critical threshold, vortices suddenly unpin and move outward, transferring angular momentum to the crust. This transfer produces the observed spin-up, often in fractions of a second. After the glitch, the system gradually relaxes as vortices repin and equilibrium is restored. Glitches vary in size and frequency. The Vela pulsar, for example, shows large glitches roughly every 3 years, with fractional increases in spin frequency of about 1 part in a million. By contrast, the Crab pulsar exhibits smaller, more frequent glitches. Other pulsars show a wide range of behaviors, from rare giant glitches to frequent microglitches. The diversity suggests that the detailed physics of vortex pinning and unpinning depends on the local conditions in each star, such as temperature, magnetic field, and crustal composition. Observationally, glitches are detected through long-term monitoring of pulsar timing. Because pulsars act as precise cosmic clocks, even tiny changes in their rotation can be measured. When a glitch occurs, the pulse arrival times suddenly shift, producing a measurable discontinuity. Careful tracking before and after the glitch allows astronomers to characterize the event in detail. The post-glitch relaxation often shows multiple timescales, indicating that different regions of the superfluid respond at different rates. This complexity supports the idea that neutron star interiors contain multiple reservoirs of angular momentum with different coupling strengths. Alternative or additional mechanisms may also play a role. In some models, crustal fractures caused by magnetic or rotational stresses can trigger glitches by suddenly changing the moment of inertia of the crust. The release stress may then unpin vortices, combining both crustal and superfluid dynamics. Magnetars, in particular, show glitches often accompanied by bursts of X-ray and gamma-ray emission, suggesting that magnetic stress in the crust contributes significantly in those cases. Thus, while the superfluid unpinning model explains many features, it is likely that multiple mechanisms operate across the diverse neutron star population. The study of glitches is valuable not only for understanding neutron stars, but also for probing fundamental physics. The behavior of superfluids under extreme conditions is difficult to reproduce in terrestrial laboratories. Neutron stars provide the only natural setting where such physics plays out on macroscopic scales. By comparing glitch statistics with theoretical models of vortex dynamics, researchers test ideas about pinning forces, crust elasticity, and the interaction between superfluids and magnetic fields. Each new glitch adds data to refine these models. Glitches also affect the use of pulsars as precise timing tools. Millisecond pulsars, which are employed in pulsar timing arrays to search for gravitational waves, are generally very stable and rarely glitch. By contrast, young pulsars prone to glitches cannot serve as stable clocks over long periods. This distinction highlights the importance of understanding glitch behavior for both astrophysical studies and applications in fundamental physics. The frequency of glitches across the pulsar population provides insight into the conditions that favor them. Young, rapidly rotating pulsars with strong magnetic fields are more likely to glitch, while old millisecond pulsars seldom do. This trend is consistent with the idea that pinning and unpinning of vortices is more efficient when the interior is warmer and the crust is more active. As neutron stars cool and age, the dynamics slow and glitches become rare. However, even in old stars, small irregularities in spin may still occur, reflecting the persistent complexity of their interiors. Recent advances in observational capability have expanded glitch studies. Large radio telescope arrays and X-ray observatories can monitor hundreds of pulsars with high precision, catching glitches in real time. In some cases, glitches have been observed to occur alongside changes in pulse profiles or emission intensity, linking interior dynamics with magnetospheric activity. These coincidences suggest that a single event in the interior can trigger both rotational and electromagnetic responses, further underlining the coupling between different parts of the star. Theoretical models continue to explore the microphysics of pinning. Calculations of the interaction between vortices and nuclear lattices suggest strong pinning forces in some regions of the inner crust. Other regions may allow easier motion, leading to differential pinning landscapes. Numerical simulations attempt to model how millions of vortices collectively behave under stress, though the complexity is enormous. Insights from condensed matter physics, where vortices in superconductors show similar collective behavior, provide useful analogies, even if the conditions are vastly different. Glitches remain an area of active research because they touch on questions that span scales from the microscopic to the cosmic. At the smallest scales, the pairing of neutrons and the structure of nuclear lattices govern vortex dynamics. At intermediate scales, the elasticity of the crust and the strength of the magnetic field influence how stresses accumulate. At the larger scales, The timing of pulses across thousands of light years reveals the final outcome. The unity of these scales makes glitches a unique astrophysical phenomenon. In conclusion, glitches demonstrate that neutron stars are not rigid, unchanging clocks but dynamic systems with rich internal physics. The sudden spin-ups and their subsequent relaxations reflect the interplay of superfluid vortices, crustal rigidity, and magnetic stresses. By observing and modelling these events, astronomers gain insight into matter at densities far beyond terrestrial reach. Each glitch is a natural experiment, briefly opening a window onto the hidden interior of a neutron star and reminding us that even the universe's most stable clocks can stutter under the weight of quantum forces and stellar gravity. The way neutron stars emit radiation across the electromagnetic spectrum is one of the keys to their detectability. From the moment of their discovery in the late 1960s, pulsars have been recognized as lighthouses of the cosmos, producing beams of radiation that sweep across the sky. The emission mechanisms are varied and complex, but they are all governed by the star's rotation, magnetic field, and surrounding plasma. The result is radiation spanning from radio waves to gamma rays, with each wavelength revealing different aspects of the neutron star environment. Radio emission is the most iconic. In the magnetosphere of a neutron star, strong electric fields accelerate charged particles to relativistic speeds. These particles travel along curved magnetic field lines, emitting coherent radio waves in the process. The radiation is beamed into narrow cones aligned with the magnetic poles. As the star rotates, these beams sweep past Earth, producing the regular pulses that gave pulsars their name. The pulse profiles vary from star to star, reflecting differences in magnetic geometry, emission altitude, and plasma conditions. Despite decades of study, the exact mechanism of coherent radio emission remains uncertain, but the basic picture of charged particles radiating in strong magnetic fields is well established. Beyond radio, many pulsars also emit in X-rays. In young pulsars, X-ray emission has both thermal and non-thermal components. The thermal component comes from the hot surface of the neutron star, still glowing from residual heat. This emission is often anisotropic because magnetic fields channel heat flow, producing hotspots at the magnetic poles. These hotspots can also be heated by returning currents from the magnetosphere, adding to the brightness. Non-thermal X-ray emission arises when accelerated particles emit synchrotron or curvature radiation in the magnetosphere. Observatories such as Chandra and XMM Newton have captured detailed X-ray profiles, showing how the pulsed emission extends across different energy bands. Gamma-ray emission adds another layer. The Fermi Gamma Ray Space Telescope has revealed that many pulsars are bright in gamma rays, often with light curves distinct from their radio pulses. The emission is thought to arise from outer regions of the magnetosphere, where particles are accelerated in vacuum gaps or current sheets. These regions produce curvature radiation, as particles follow curved magnetic field lines at near light speeds. Gamma-ray pulsars demonstrate that high-energy processes dominate in some neutron stars, even when radio emission is weak or absent. This diversity emphasizes that the magnetosphere is a dynamic environment with multiple sites of particle acceleration. The beaming of emission is central to observations. A neutron star may radiate strongly, but if its beam does not cross Earth, it remains invisible as a pulsar. This selection effect explains why the observed pulsar population represents only a fraction of all neutron stars. Estimates suggest that the Milky Way may contain hundreds of millions of neutron stars, yet only a few thousand are detected as pulsars. The rest either beam away from us or emit too faintly to be observed. Pulse profiles carry rich information. By measuring the arrival times of pulses with high precision, astronomers can track spin rates, spin down, and irregularities. The shape and width of pulses reveal the geometry of the emission region and the orientation of the magnetic and rotational axes. In some pulsars, polarization measurements across the pulse provide maps of the magnetic field structure. The combination of timing, intensity, and polarization makes pulsar emission a powerful diagnostic of neutron star magnetospheres. Some neutron stars exhibit mode changes or nulling, where the emission switches off for periods ranging from seconds to days before resuming. These behaviors suggest that the magnetosphere can reorganize itself, altering plasma conditions and emission patterns. In rare cases, intermittent pulsars switch between radio loud and radio quiet states, with corresponding changes in spin-down rate. These transitions demonstrate the close coupling between magnetospheric currents and the rotational dynamics of the star. Millisecond pulsars, which are old neutron stars spun up through accretion, often emit across multiple bands as well. Their radio pulses are exceptionally stable, allowing their use as cosmic clocks, but many also show X-ray and gamma-ray emission. The combination of weak magnetic fields and rapid rotation produces distinct magnetospheric structures compared to young pulsars. The discovery of gamma-ray millisecond pulsars by Fermi has expanded our understanding of emission processes under different conditions. In magnetars, emission is dominated by magnetic field decay rather than rotation. Their persistent X-ray emission comes from crustal heating by magnetic stresses. In addition, they produce bursts and flares in X-ray and gamma-ray bands, sometimes reaching extreme luminosities. The giant flare of 2004 from the magnetar SGR 180620 was so bright that it briefly saturated detectors on satellites and was detectable even after scattering off Earth's atmosphere. These events illustrate the immense energy stored in magnetic fields and their ability to power explosive emission far exceeding spin-down power. Accreting neutron stars in binaries present another set of emission phenomena, as matter from a companion star falls onto the neutron star. It is funneled by magnetic fields onto the poles, producing bright X-ray emission. In some cases, this emission is pulsed, making them X-ray pulsars. The accretion process can dominate the luminosity, outshining the thermal emission from the surface or magnetospheric emission. Observations of X-ray bursts, caused by thermonuclear flashes on the surface, add further complexity. Thus, emission depends not only on the intrinsic properties of the neutron star, but also on its environment. The study of emission across bands is a collaborative effort among different observatories. Radio telescopes such as Arecibo, Parkes, and FastMap pulsar populations, X-ray missions like Chandra, NICER, and XMM Newton resolve surface hotspots and thermal spectra. Gamma-ray telescopes such as Fermi uncover high-energy pulsars invisible at lower frequencies. Together, they provide a multi-wavelength view that unifies the picture of neutron star emission. Each band highlights different physical processes, from coherent plasma effects to thermal surface emission to high-energy particle acceleration. The theoretical challenge is to integrate these observations into a coherent framework. Models of pulsar magnetospheres incorporate relativistic plasma physics, electrodynamics, and radiation processes. Despite progress, uncertainties remain about the exact locations and mechanisms of emission. Are radio pulses generated close to the surface or higher in the magnetosphere? Are gamma rays produced in outer gaps or in current sheets? These questions continue to drive research. with each new discovery adding constraints. In summary, neutron star emission is diverse, spanning radio to gamma rays and powered by rotation, magnetic decay, or accretion. The beams and pulses reveal geometry and magnetospheric physics. Thermal and non-thermal components combine to produce complex spectra. Variations such as nulling and mode changes show that magnetospheres are dynamic and responsive. Multi-wavelength observations and theoretical models together reveal a rich picture, though open questions remain. What is clear is that neutron stars, though compact and invisible in ordinary light, broadcast their presence across the spectrum, providing astronomers with signals that can be studied in remarkable detail. While many neutron stars evolve in isolation, a significant fraction belong to binary systems. In these environments, the gravitational pull of the neutron star influences its companion, and in some cases matter flows from one star to the other. This exchange of mass profoundly alters the life history of the neutron star, leading to phenomena such as accretion-powered emission, spin-up into millisecond pulsars, and the recycling of old stars into luminous new objects. Accretion begins when a neutron star's companion star expands or loses matter through stellar winds. If the companion fills its Roche lobe, gas flows through the inner Lagrange point toward the neutron star. The infalling matter forms an accretion disk around the compact star, gradually spiraling inward under the influence of viscosity. As the material approaches the neutron star, gravitational energy is converted into heat, producing intense X-ray emission. In this way, accreting neutron stars shine far more brightly than they would in isolation, with luminosities that can rival or exceed those of entire galaxies when considered collectively. The accretion process is strongly influenced by the neutron star's magnetic field. In stars with strong fields, the inner accretion disk is disrupted at the Alphen radius, where magnetic pressure balances the ram pressure of infalling gas. From this point inward, material is funneled along magnetic field lines onto the magnetic poles, producing hotspots on the surface. As the star rotates, these hotspots generate X-ray pulses, leading to the discovery of X-ray pulsars in the 1970s. Observations of X-ray pulsars have provided detailed information about accretion geometry, magnetic field strength, and neutron star spin. In some systems, accretion is unstable, leading to bursts of X-rays rather than steady emission. These thermonuclear bursts occur when accumulated hydrogen and helium on the surface ignite in runaway fusion. Within seconds, the neutron star brightens dramatically before fading over minutes. Such X-ray bursts provide direct evidence of nuclear processes occurring on neutron star surfaces and allow measurements of fundamental parameters such as surface gravity and composition. Recurrent bursts have been used to probe the thickness of accreted layers and the rate of fuel accumulation. Long-term accretion can also change the spin of the neutron star. As matter carrying angular momentum falls onto the star, it spins the neutron star up, reducing its rotation period. This recycling process transforms old, slow neutron stars into millisecond pulsars, with spin periods as short as a few milliseconds. The discovery of such pulsars confirmed the recycling scenario, showing that accretion can rejuvenate a neutron star and extend its observable lifetime. Millisecond pulsars are exceptionally stable rotators, making them valuable tools for precision timing. Their origin in binary accretion links stellar evolution to fundamental physics applications. The end state of some binary systems is the so-called black widow or redback pulsar. In these systems, the neutron star has been spun up by accretion and now emits a strong pulsar wind that gradually evaporates its companion. The companion star is whittled down to very low mass, sometimes only a fraction of a solar mass. Observations of such systems reveal the ongoing battle between the pulsar's energetic wind and the gravitational hold of the companion. The dynamics of these binaries provide insights into the interplay of accretion, evaporation, and binary evolution. Binary interactions also produce observable variability. In some accreting systems, changes in mass transfer rate lead to alternating periods of brightness and quiescence. During quiescent phases, the neutron star crust cools after being heated by nuclear reactions during active accretion. Monitoring the cooling provides information on the thermal conductivity and composition of the crust. During active phases, X-ray emission dominates, allowing astronomers to measure accretion rates and magnetic field interactions. The cyclic nature of these systems makes them natural laboratories for studying the response of neutron stars to changing environments. Not all binary neutron stars accrete matter. In double neutron star systems, both stars are compact remnants, and their interaction is dominated by gravitational forces rather than mass transfer. These systems gradually lose energy through the emission of gravitational waves, spiraling inward until they eventually merge. Observations of double neutron star binaries, such as the Hulse-Taylor pulsar discovered in the 1970s, confirmed the predictions of general relativity by showing orbital decay consistent with gravitational wave emission. These systems are precursors to the mergers detected by LIGO and Virgo, linking binary evolution to some of the most energetic events in the universe. The population of binary neutron stars reveals the diversity of outcomes. Some neutron stars accrete from high-mass companions through stellar winds, producing bright but short-lived X-ray binaries. Others accrete from low-mass companions through Roche lobe overflow, creating low-mass X-ray binaries that can persist for billions of years and recycle neutron stars into millisecond pulsars. Some binaries evolve into double neutron stars, eventually merging. Each pathway reflects the complex interplay between stellar mass, orbital separation, and evolutionary timescales. Accreting neutron stars also serve as probes of strong gravity. The matter falling onto the surface releases energy in a deep gravitational potential, producing X-ray spectra shaped by relativistic effects. Features such as broadened ion lines in X-ray spectra provide evidence for relativistic Doppler shifts and gravitational redshift near the neutron star. Quasi-periodic oscillations observed in X-ray flux are thought to reflect orbital motion in the innermost regions of accretion disks, providing constraints on neutron star masses and radii. These phenomena allow astronomers to study general relativity in regimes inaccessible elsewhere. The study of binary neutron stars is enriched by multi-wavelength observations. Optical telescopes can track the motion of companion stars, allowing dynamical mass measurements. Radio timing of pulsars provides precise orbital parameters. X-ray observatories monitor accretion and bursts. Together, these data reveal the full picture of binary evolution, from mass transfer and spin-up to eventual merger. Each binary system is a case study in how compact objects interact with their environment, and collectively they illustrate the versatility of neutron stars as astrophysical laboratories. In summary, binary evolution profoundly shapes the lives of many neutron stars. Through accretion, they are spun up, heated, and transformed into new observational classes. Through mergers, they produce gravitational waves and heavy elements. Through interactions with companions, they reveal processes ranging from nuclear burning on surfaces to orbital decay under general relativity. Neutron stars in binaries are not solitary remnants but active participants in stellar ecosystems, demonstrating how compact objects influence and are influenced by their companions across cosmic timescales. When two neutron stars exist in a close binary system, their orbit gradually shrinks because of gravitational wave emission. General relativity predicts that accelerating masses radiate energy as ripples in space-time, and in the case of compact binaries, this radiation removes orbital energy. The binary pulsar discovered by Russell Hulse and Joseph Taylor in 1974 provided the first indirect proof of this effect. The orbital period of that system was observed to decrease over time exactly as predicted by Einstein's theory. Decades later, gravitational wave observatories directly detected the mergers of neutron stars, confirming both the theory and the astrophysical expectations. As the orbit decays, the stars spiral closer together. In the final minutes before merger, the orbital period shrinks to milliseconds, and gravitational wave emission rises steeply in frequency and amplitude. The waveform encodes information about the masses and internal structure of the stars. The tidal deformation each star experiences alters the phase of the gravitational wave signal, providing a probe of the equation of state of dense matter. Thus, mergers offer one of the most powerful ways to study neutron star interiors. The most famous event so far is GW17087, detected in August 2017. Two neutron stars with a combined mass of about 2.7 solar masses merged in a galaxy 130 million light-years away. The gravitational wave signal was observed by the LIGO and Virgo detectors, and within seconds, gamma-ray satellites detected a short burst of gamma rays from the same region. Over the following days and weeks, telescopes across the electromagnetic spectrum tracked the evolving light from the event, known as a kilonova. This was the first time both gravitational waves and electromagnetic radiation were observed from the same source, inaugurating the era of multi-messenger astronomy. The kilonova emission arises from the radioactive decay of heavy elements created in the merger ejecta. As the two neutron stars collide, tidal forces and shocks expel matter into space. This neutron-rich material undergoes rapid neutron capture, known as the R process, forming heavy elements such as gold, platinum, and uranium. As these unstable nuclei decay, they release heat that powers the optical and infrared glow of the kilonova. The observed colours and brightness of GW17087 matched predictions of R-process nucleosynthesis, confirming that neutron star mergers are major sites of heavy element production in the universe. The gravitational waves also revealed details of the remnant formed after the merger. Depending on the total mass and the equation of state, the merged object can be a hypermassive neutron star temporarily supported by rapid rotation and thermal pressure, or it may collapse quickly into a black hole. In GW17087, the absence of long-lasting X-ray or radio signals suggested that the remnant collapsed within seconds to a black hole. Such outcomes help refine estimates of the maximum neutron star mass, linking mergers directly to the stability limits discussed earlier. Subsequent observations have expanded the sample. Other gravitational wave events have included possible neutron star mergers and neutron star black hole mergers. Each detection adds constraints on population statistics, merger rates, and the diversity of outcomes. By comparing multiple events, astronomers can estimate how frequently mergers occur in the universe and how much heavy element production they contribute. Current estimates suggest that mergers alone may account for much of the R-process material observed in the Milky Way. Mergers also produce energetic outflows and jets. In GW17087, a relativistic jet produced a short gamma-ray burst, followed by afterglows in X-ray, optical, and radio wavelengths. Observations of the afterglow revealed that the jet was initially off-axis relative to Earth, but as it slowed and spread, its emission became visible. This provided the first clear link between short gamma-ray bursts and neutron star mergers. Such events explain how compact object collisions can drive some of the most luminous explosions in the universe. The role of gravitational wave astronomy continues to grow. With each new observing run, LIGO, Virgo, and Kagra are expected to detect dozens of compact object mergers. The precision of these detections will improve, allowing better measurements of tidal deformability and thus of the neutron star equation of state. Future observatories such as the Einstein Telescope and Cosmic Explorer will extend sensitivity, enabling detections out to much greater distances and providing large samples for statistical studies. Gravitational wave astronomy thus opens a new avenue for exploring both astrophysics and fundamental physics. In addition to revealing dense matter physics, mergers test general relativity under extreme conditions. The waveforms from inspiral and merger match predictions of Einstein's equations with remarkable precision. Any deviations could hint at new physics or modifications to gravity. So far, no significant deviations have been found, reinforcing the robustness of general relativity. At the same time, mergers probe nuclear physics, astrophysics, and cosmology simultaneously, uniting multiple fields of science in a single observation. Electromagnetic follow-up remains essential. Gravitational waves provide the masses and orbital dynamics, while electromagnetic signals reveal the outflows, composition, and environment. Coordinated campaigns across observatories have demonstrated the power of multi-messenger astronomy. The success of GW1-708-1-7, with contributions from hundreds of instruments worldwide, highlights how collaborative efforts can capture the full story of such cosmic events. The light curves of Novae, the spectra of ejecta, and the morphology of afterglows all provide complementary data that cannot be extracted from gravitational waves alone. The astrophysical importance of neutron star mergers extends beyond individual events. They contribute to the chemical evolution of galaxies by enriching the interstellar medium with heavy elements. They influence the population of compact objects and the formation of black holes. They also serve as standard sirens for cosmology by measuring the gravitational wave signal directly. Astronomers can estimate distances without relying on traditional distance ladders. Combined with redshift measurements of host galaxies, mergers provide independent constraints on the expansion rate of the universe, offering insight into the Hubble constant tension. In summary, neutron star mergers are among the most dramatic and informative events in the cosmos. They generate gravitational waves, short gamma-ray bursts, colonovae, and heavy elements, all in a matter of seconds to days. They test general relativity, probe nuclear physics, and enrich the universe with the raw materials for planets and life. Each new detection deepens our understanding of these collisions and reinforces the interconnectedness of astrophysical processes. Neutron star mergers thus stand as cornerstones of modern multi-messenger astronomy, bridging theory and observation in ways unimaginable only a generation ago. One of the profound consequences of neutron star mergers is the creation of heavy elements through rapid neutron capture, known as the R process. Ordinary stellar nucleosynthesis, occurring in the cores of stars and during supernova explosions, produces elements up to iron efficiently and elements somewhat heavier than iron through slower processes. But many of the heaviest elements in the periodic table, including gold, platinum, and uranium, require environments with vast numbers of free neutrons available in a short time. The conditions of a neutron star merger provide exactly that environment. When two neutron stars collide, tidal forces and shocks eject matter into space. This matter is composed primarily of neutrons and neutron-rich nuclei. the building blocks for rapid neutron capture. In the expanding ejecta, densities remain high enough for nuclei to absorb neutrons much faster than they can undergo radioactive decay. As a result, nuclei quickly climb the chart of Euclides to very heavy, unstable isotopes. Once the supply of neutrons diminishes, these isotopes undergo a cascade of beta decays, converting neutrons into protons and moving the nuclei towards stability. This chain of reactions produces the familiar heavy elements observed on Earth and in the solar system. The R process in mergers is supported by both theoretical modeling and observational evidence. Simulations show that as much as 1/100th of a solar mass of material can be ejected in a single event, with a composition dominated by neutron-rich matter. When this material undergoes radioactive decay, it produces heat that powers the kilonova emission, observed in optical and infrared wavelengths. The brightness and color of the kilonova depend on the composition of the ejecta. Lanthanides, a group of heavy elements with complex electron structures, increase the opacity of the material, making the emission redder and longer lasting. Observations of G boson and 717 revealed both a blue component associated with ejecta pore in lanthanides and a red component associated with lanthanide-rich material, confirming that different regions of the ejecta contribute to a variety of heavy elements. The significance of this discovery is immense. For decades, the origin of the heaviest elements was debated. Core collapse supernovae were once thought to be the primary site of R-process nucleosynthesis, but detailed models struggled to produce sufficient amounts of heavy elements. Neutron star mergers, by contrast, naturally provide the necessary conditions and quantities. The kilonova observation following GW70817 provided direct evidence that mergers contribute substantially to the galactic inventory of heavy elements. The amount of gold and platinum alone synthesized in that single event was estimated to be many times the mass of Earth. Heavy element production by mergers has implications for galactic chemical evolution. Over billions of years, successive mergers enrich the interstellar medium with R-process material. Stars forming from this enriched gas inherit the heavy elements, which later become incorporated into planets and, eventually, into living organisms. The presence of uranium and thorium on Earth, which contribute to geothermal heat through radioactive decay, may owe its origin to long-past neutron star mergers. Thus, these cosmic collisions have direct relevance to planetary habitability and the conditions for life. Observational astronomy has begun to trace this history. By measuring the abundances of heavy elements in old stars in the Milky Way halo, astronomers reconstruct the enrichment history of the galaxy. Some ancient stars show extreme enhancements of R-process elements, suggesting they formed from gas enriched by one or a few merger events. Others show lower abundances, reflecting more mixed contributions. These chemical fingerprints provide indirect but compelling evidence for the role of mergers over cosmic time. Another tool is the study of short gamma-ray bursts, which are now firmly linked to neutron star mergers. Observations of their host galaxies show that such events occur in a variety of environments, from young, star-forming galaxies to older, elliptical galaxies. This diversity suggests that mergers can occur both quickly after star formation and after long delays, depending on the binary's orbital decay time. Consequently, R-process enrichment can happen at different stages of galactic evolution, spreading heavy elements widely. Theoretical work continues to refine estimates of how much material is produced per merger. The total yield depends on factors such as the masses of the neutron stars, the equation of state of dense matter, and the geometry of the merger. Some matter is ejected dynamically during the collision, while additional outflows arise from accretion disks around the remnant. Each component may have different compositions and contribute differently to the overall nucleosynthesis. Simulations now incorporate detailed nuclear reaction networks, tracking thousands of isotopes to predict abundance patterns. These predictions are compared with solar system abundances and with stellar observations, gradually converging on a consistent picture. The detection of multiple kilonovae in the future will provide more data to test these models. Each event offers a laboratory for studying our process nucleosynthesis in action. Spectroscopy of kilonova light will reveal absorption features of newly formed elements. Although the complexity of heavy element atomic structures makes interpretation challenging, nonetheless, improvements in atomic data and observational capability are steadily advancing this field. With the growing sensitivity of telescopes, the ability to capture kilonovae at greater distances will expand the sample and refine statistical estimates of heavy element production. The cosmological importance of our process production extends beyond individual galaxies. In the early universe, before the first mergers occurred, only lighter elements existed, forged in the Big Bang and in the first generations of stars. The enrichment of the cosmos with our process elements is a gradual process tied to the life cycles of stars and binaries. By observing galaxies at different redshifts, astronomers trace how heavy element abundances evolve over time. These studies connect the physics of neutron star mergers to the large-scale history of the universe. In practical terms, the presence of our process elements on Earth illustrates the cosmic chain of events. The gold in jewelry, the uranium in reactors, and the platinum in electronics all owe their existence to violent collisions of neutron stars billions of years ago. The radioactive heat from thorium and uranium influences Earth's geology, driving mantle convection and plate tectonics. Without these elements, the planet might lack the dynamic surface and long-lasting magnetic field that helps sustain life. Thus, the astrophysical processes of mergers and nucleosynthesis extend their influence into geology and biology. In conclusion, neutron star mergers are not only sources of gravitational waves and gamma-ray bursts, but also forges of the heaviest elements in the universe. Through rapid neutron capture, they produce gold, platinum, uranium, and many other elements, enriching galaxies and shaping the composition of planets. Observations of kilonovae have confirmed this role, and ongoing studies of stellar abundances and merger rates continue to refine our understanding. The link between the most violent stellar collisions and the material foundation of life and technology underscores the profound connections that neutron stars create across scales of time, space, and matter. Neutron stars are not only laboratories for extreme physics, but also extraordinary clocks. The discovery of pulsars in 1967 revealed that the regular pulses of radio emission could be timed with remarkable precision. Some pulsars rival or surpass the stability of atomic clocks over long periods, making them cosmic timekeepers. The key lies in their rotation. Once a neutron star is formed, its rotation period is governed by conservation of angular momentum, and despite gradual spin down, the pulses arrive with predictable regularity. By monitoring these pulses, astronomers can measure time intervals, track orbital dynamics, and even probe gravitational waves. Ordinary pulsars, with rotation periods ranging from fractions of a second to a few seconds, already demonstrate remarkable regularity. However, millisecond pulsars stand out as the most precise. These are old neutron stars that have been spun up by accretion in binary systems. With periods of 1 to 10 milliseconds, they rotate hundreds of times per second, and their stability rivals that of laboratory clocks. Timing measurements show that the arrival times of pulses from millisecond pulsars can be predicted to within microseconds over decades. This extraordinary stability allows them to serve as tools for fundamental physics. One application is the study of binary systems. By timing pulsars in binaries, astronomers can measure orbital parameters with exquisite precision. The Hulse-Taylor binary pulsar, discovered in 1974, demonstrated this capability. Its orbital decay matched predictions of gravitational wave emission, providing the first indirect evidence for gravitational waves and earning the Nobel Prize in Physics. More recently, pulsars in relativistic binaries have been used to test general relativity under strong field conditions, verifying phenomena such as Shapiro delay, gravitational redshift, and relativistic precession. These tests confirm the theory's accuracy and constrain possible deviations. Another application is in pulsar timing arrays. By monitoring an ensemble of millisecond pulsars spread across the sky, astronomers can search for correlated deviations in pulse arrival times caused by gravitational waves passing through Earth. These waves, produced by supermassive black hole binaries and other cosmic sources, have frequencies too low for ground-based detectors like LIGO, but fall within the sensitivity of timing arrays. The detection of a stochastic gravitational wave background using pulsar timing data, reported in 2023 by multiple international collaborations, represents a major step forward in gravitational wave astronomy. This result demonstrates that pulsars can act collectively as a galaxy-scale observatory, sensitive to phenomena occurring billions of light-years away. Pulsars also provide natural laboratories for measuring fundamental constants and testing alternative theories of gravity. Because their timing is so precise, even tiny perturbations in their environment can be detected. For instance, the presence of planets around pulsars has been inferred from periodic variations in pulse arrival times. The first confirmed exoplanets were discovered in this way around the millisecond pulsar PSR B112 in the early 1990s. Timing has also revealed triple systems, hierarchical binaries, and other complex configurations that test gravitational dynamics in unique regimes. The precision of pulsar clocks arises from the stability of their rotation and from the coherence of their emission mechanisms. Although some pulsars exhibit irregularities such as glitches or timing noise, millisecond pulsars are exceptionally stable. Their low magnetic fields and advanced ages reduce internal disturbances, while their rapid rotation averages out fluctuations. This stability has been harnessed for practical purposes, including proposals to use pulsars as natural navigation beacons for spacecraft. By comparing observed pulse arrival times with predicted ephemerides, a spacecraft could determine its position autonomously, much like GPS but on a galactic scale. Observational techniques continue to improve pulsar timing accuracy. Large radio telescopes such as FAST in China, Arecibo before its collapse, and Parkes in Australia have long monitored pulsars with high sensitivity. New facilities like the Square Kilometre Array will expand the sample and precision dramatically. At the same time, X-ray missions like NICER provide complementary timing measurements in high-energy bands, allowing cross-checks and new applications. Together, these instruments enhance the role of pulsars as cosmic clocks. The long-term monitoring of pulsars has built a dataset spanning decades. These records reveal not only steady spin-down but also subtle variations linked to processes in the star's interior and magnetosphere. By modelling these variations, astronomers gain insights into superfluid dynamics, magnetic field evolution, and external torques. In this sense, Pulsar timing is not just a tool for astrophysics beyond neutron stars, but also a direct probe of the neutron stars themselves. Each timing residual carries physical meaning about the interplay of forces inside and around the star. Pulsars also contribute to cosmology. The use of pulsar timing arrays as standard sirens, analogous to gravitational wave detections, may help constrain cosmological parameters. In addition, the distribution of pulsars across the Milky Way informs models of star formation, supernova rates, and galactic structure. The detection of pulsars in globular clusters provides information about dense stellar environments and binary interactions. Each application underscores the versatility of pulsar clocks. The link between pulsars and timekeeping also carries philosophical weight in physics, though the focus here remains observational. Time itself, as measured on Earth, is tied to atomic transitions. In the cosmos, it can be measured by the steady turning of neutron stars, remnants of massive stellar explosions. The agreement between these very different clocks, terrestrial atomic standards, and astrophysical pulsars demonstrates the universality of physical laws. The pulses arriving across thousands of light years remain synchronized to within microseconds, confirming that the behavior of matter and spacetime is consistent throughout the observable universe. Looking ahead, the role of pulsars as cosmic timekeepers will continue to expand. With more sensitive telescopes, more millisecond pulsars will be discovered, enriching timing arrays and improving sensitivity to gravitational waves. Multi-messenger astronomy will integrate pulsar timing with gravitational wave detections, electromagnetic observations, and even neutrino studies. The stability of pulsar clocks ensures they will remain central to these efforts. Whether probing the interiors of neutron stars, testing general relativity, mapping the galaxy, or detecting distant black hole mergers, pulsar timing exemplifies the precision and reach of astrophysics. In conclusion, pulsars transform neutron stars from compact remnants into cosmic chronometers. Their regular pulses provide tools for studying gravity, dense matter, galactic structure, and cosmology. Millisecond pulsars in particular achieve stability unmatched by any other natural system, enabling applications from exoplanet discovery to gravitational wave detection. They embody the dual nature of neutron stars, extreme laboratories of dense matter and precise beacons of time. In the quiet regularity of their pulses, across immense distances and timescales, neutron stars demonstrate the profound order underlying even the most violent remnants of stellar death.